Astronomers believe our solar system began in a swirling tempest of gas and dust. From this chaos, the planets were born, each unique, each with its own story to tell.
When we study the planets, we like to make comparisons between those planets and our own planet, Earth. We can see the processes that take place on the Earth also acting on other planets.
The physics, the chemistry, all operate the same on all the different planets. And there are more examples on the other planets than just on the Earth alone of these processes. And so we always learn by looking outward and seeing what's going on the other worlds as well.
To truly understand these other worlds, we must first examine the forces that formed and continue to shape planet Earth.
We think that all planets, including Earth, formed by the collision of smaller bodies. These bodies were all in orbit around the sun. They were colliding with each other, building progressively bigger objects. As this body formed, it was severely heated by the impacts. Because of that severe heating, it started to melt, and as it melted, it differentiated, with light material coming to the surface and heavy material, such as the iron core, sinking to the center.
It was above the melting point, and therefore was a fluid, and the inside of the Earth crystallized slowly out of the magma ocean as it cooled and grew. And the present Earth is the remnant of what was initially a very hot beginning.
In this very early period of the history of the Earth, which lasted only 100 million years, a tremendous amount of energy was released, and the conditions were very traumatic, violent even, because of these continuing impacts. In this early stage, we might think of the Earth as being almost completely molten.
In fact, we have no evidence whatsoever of the first 1 billion years of the Earth's existence, because all of these rocks have disappeared and presumably been redissolved in a molten magma ocean. Since that time, the Earth's been cooling down and differentiating into a crust and a mantle and a core, which are the three main subdivisions of the Earth.
We have a core, which is mostly liquid iron, and surrounding that core there is a mantle of rock similar to the rocks we see at the surface of the Earth. Part of that rock is a very thin layer that we call the crust, which is a little different in composition and sits on top because of its lower density. The Earth has a quite large magnetic field, and we believe that nearly all of that field is created in the iron core, not because it is made of iron so much as because it is a liquid metal, and the motion of that liquid metal is able to create the field.
Magnetic fields on Earth have been known from at least early Chinese times, that lodestone would point in a north or south direction. And then when the early exploration of the Arctic took place in the last century and before, one of the big tasks was to find out where North Magnetic Pole is. And it's not the same place as the North Geometric Pole, the spin axis. And that's been quite a mystery. Furthermore, it moves. It's not always the same place. You have to keep correcting the tables. So we're looking at something dynamic. It's not fixed like the Earth's spin, but it's much more dynamic. We can't drill down to that depth, but the belief is somehow it has to do with the Earth's core, the iron core, which is a conductor, and somehow there must be movement.
When you have a liquid metal that is circulating, convecting, it is able to create a magnetic field by what is called a dynamo process. In fact, the Earth's magnetic field is telling us about the liquid character of the core and about the fact that it is in motion.
While our planet's magnetic field offers strong evidence of a molten core, scientists learn even more from the movements of the Earth itself.
You can see power lines are swaying.
It's a real tough question about how to image or see the outside of a planet, the skin, and then imagine what might be going on inside. But fortunately, from studying the Earth, we have some pretty good ideas, because there we have a lot more information. We have seismic waves that go deep into the Earth. We have gravity fields around it and so forth.
Seismology is the best method we have for determining what the structure of the inside of the Earth is. And earthquakes, although they can be very destructive, they provide a lot of energy, and seismologists have seismometers all over the surface of the Earth, mainly in the continental regions. And these pick up waves from earthquakes, including waves that bounce off the core, that bounce off the other side of the Earth.
These waves, which are produced naturally by earthquakes, can be picked up at the other side of the Earth, and their arrival times very precisely measured. And by knowing through laboratory study the speed of waves in different kinds of materials, we can then work out what the inside of the Earth is made of.
The waves of motion created by earthquakes not only tell us about our planet's interior, they reveal the dynamic nature of the Earth's crust.
There's lots of different reasons why you wouldn't expect continents to be stationary on the surface of the Earth, or plates, in fact, to remain motionless. The interior of the Earth is very close to its melting point, and therefore it has a very low viscosity. You can think of it as warm asphalt or warm wax. It has the consistency of a very low viscosity fluid, and therefore flows readily, although certainly not as readily as water. If there's temperature gradients in the Earth, if there's places that are hot because they've been covered by a supercontinent, and there's other places that are cold because they have been cooled down by a very cold material that was at the surface of the Earth sinking into the mantle, then we set up currents which tend to move continents around.
The process is one of convection. It is the same thing that happens if you take a pot of soup and put it on the stove and heat it up, and you create a circulation of the fluid. In just the same way, the inside of the Earth, which is still very hot, although mostly solid, is undergoing this convection. The heating is coming from the decay of radioactive elements, uranium, thorium, and potassium for the most part. And this is creating hot and cold regions inside the Earth. And just as a hot air balloon rises in the Earth's atmosphere, so hot rock, solid rock, but hot rock can flow up. And as part of the circulation, we see at the surface of the Earth the sideways movement of material.
What we're seeing now on the surface of the Earth is actually a fairly unique situation, where we've had a supercontinent that just in fairly recent geological time broke up. If you can imagine North America and Europe being attached to the northern part of Africa, South America being attached to the southern part of Africa, and then Antarctica and Asia and India and Australia clustering around the southern and the eastern part of Africa, then we have the supercontinent of Pangaea. It lasted for perhaps 200 million years, and then for some reason it broke up and all the pieces dispersed.
People used to talk about continental drift as though the most important part of that motion was just the continents themselves. We now know that, in fact, the most important place to look is on the ocean floor, because it is there where we see the processes responsible for these movements.
Seafloor spreading is the phrase used to describe the fact that a new ocean floor is being generated at mid-ocean ridges continuously. And these mid-ocean ridge basalts are moving out and away from the mid-ocean ridge, and the mid-ocean ridges themselves are pushing the continents apart. So seafloor spreading just describes the fact that the crust of the seafloor and the mantle under the crust is not stationary, it's not static, it's constantly being generated, and just like a conveyor belt, the new crustal material is being spread away from the mid-ocean ridge.
We see it in the middle of the Atlantic. We see it out in the middle of the Pacific as places where new material is being made on the surface of the Earth. And of course, since this is a circulation, it has to go down somewhere, and the material, once it has cooled off, is sinking back down into the Earth in places that we call subduction zones. The Aleutian Islands ride on top of a subduction zone. Another example is Japan and south of Japan, and also off the coast of Chile. There is a subduction zone going under South America. So this is all part of a giant circulating system, all part of mantle convection, all part of what we would call a heat engine.
This massive heat engine buckles continents, pushes up mountain ranges, and builds internal pressures that can erupt in a fury of heat and molten rock.
Volcanism is a very important process in some planets, particularly the so-called terrestrial planets. It's very important on Earth, as we know, because of its big thermal engine, but may also be important on planets such as Venus or Mars. These volcanic emanations, where magma comes out of the Earth, produce very interesting surface features, such as the great mountain chains that we see in conical mountains. They produce hot spots, such as Hawaii. These are individual islands of volcanic material, but there are also hotspot traces such as the Yellowstone hotspot trace. So many features that we see on Earth are volcanic in nature.
When you look at the surface of the Earth, you see rocks that come up from the inside of the Earth. In most cases, it's only a short distance from inside the Earth, in fact, perhaps 100 kilometers. These rocks are often volcanic. They started as liquid and rose up in a volcanic process, flowing onto the surface of the Earth where they froze. We see in the structure at the surface of the Earth changes brought about by the motion inside the Earth. So one of the most important things we learn at the Earth's surface is the dynamic nature of the Earth, the movement of continents, the creation of new seafloor through this volcanic process, an endless cycle of material being brought to the surface and taken back down again.
It is this cycle of renewal that has forever destroyed evidence of our planet's violent beginning.
A fundamental question in comparative planetology is why the Earth is not heavily cratered in the same way that the Moon is, for example, or Mars. Well, the real simple answer here is not that we've led a charmed life, but rather that the evidence for all of this cratering is long since disappeared on the Earth. Much of the cratering probably occurred in the early part of the history of the solar system, and with plate tectonic processes going on with cyclic rates of about one cycle in 200 or 300 million years, we very quickly, again within the context of the several billion-year-old age of the solar system, we very quickly wipe out evidence for this early cratering history of the Earth.
Ever since the planetary exploration program started, we've been looking at the other terrestrial planets to see evidence for plate tectonics. And so far it turns out that every planet is absolutely unique, and the Earth is probably the most unusual in having evidence for large-scale motions of the plates.
On other planets, we will expect to have the same processes, but interestingly, part of it seems to be different. The surface motion is much less on other planets. We don't see the subduction zones, the other part of the circulation, and so we don't think that the material is being continuously recycled. So remarkably, the Earth is at the moment the only planet we know that manages to do this very efficient, continual recycling many, many times over through Earth history.
Except for seismology, most of the evidence we have about the deep interior of the Earth is from the surface. And there's a balance between these interior forces, which cause volcanoes and mid-ocean ridges and mountains, and exterior forces, which cause erosion. So atmospheric processes and rivers continuously degrade mountains and coastlines, and plate tectonics is constantly regenerating these. If either one of these mechanisms was to turn off, the Earth would be quite a different place. And because the Earth has a hydrosphere, has running water, has an atmosphere, as well as interior dynamics, molten lava, which comes to the surface, we can expect the Earth to be quite different from some of the other terrestrial planets.
Just as the continual recycling of the Earth's crust makes it unique among the planets, so too does the thin layer of gas and liquid that clings to its surface.
One of the most unique attributes of the Earth, particularly if you're a human being, is the fact that the Earth has oceans and has water and has an atmosphere. It turns out that it's very difficult to have a planet where the conditions are appropriate for water. It's a very narrow temperature range, from 0 centigrade to 100 centigrade. If the surface of the planet doesn't fall in that particular range, then it won't be able to retain liquid water.
The Earth seems to hold a very favorable position in the solar system with regard to its distance from the sun. It's just far enough away so that it's cool enough that the oceans could condense from the original water vapor that was deposited on the Earth, and that came out from the inside of the Earth by outgassing. Yet it's not far enough away such that the water eventually would freeze over and the planet would be basically an ice ball.
Well, the Earth is unique among planets in our solar system in many ways, but perhaps one of the most important ways that it differs is in the amount of water which currently covers the Earth. Roughly 75% of the Earth is covered by ocean waters. One of the most interesting questions faced by Earth scientists is understanding how oceans or water came to exist at the surface of our planet. Well, perhaps the water was bound up in the compounds which made up the early particles that formed the planet, and they were released later in the evolution of the Earth. It's one of the most important mechanisms for bringing water vapor to the surface of the planet is through volcanic eruptions. We know, for example, today that water makes up a large component of the volatile elements that come out in volcanic eruptions.
Continuous venting of the Earth's interior also played a key role in the formation of its atmosphere.
The origin of the Earth's atmosphere is fairly complicated. There were developments early in the history of the Earth and then developments that occurred later. When the Earth first formed by accretion, of course, there were primordial gases that accreted with the Earth. These consisted of large amounts of helium, hydrogen, and so on. A lot of these gases were eventually lost by simply being blown away by the solar wind blowing through the solar system. Then there was a later epoch where volatile gases came out from the interior of the Earth by volcanism and other processes where the interior of the Earth was overturning or convecting.
But it's still not completely clear whether all of the present atmosphere of the Earth and Venus, for example, came from the present interior, or whether it's possible that a secondary atmosphere can form by the impact of comets. It's still controversial. We still don't know if most or all of the volatiles, even in the case of the Earth, were brought in after the planet itself formed, or whether a slow, continuous degassing process is still happening today to remove the volatiles from the interior.
We think that after the Earth formed, the material that made up the Earth had a small amount of gas as part of the rock, but during the melting of the Earth, some of that gas escaped, as indeed it does right now in volcanoes such as Hawaii, where we see water as steam and carbon dioxide coming out of the volcanoes at the same time as the lava flows flow down the side of the mountain. On the early Earth, these processes of bringing gas out of the interior were much more extensive, much stronger, and so we think that it is quite likely that you could build up a dense atmosphere, probably of carbon dioxide early on.
In time, the Earth cooled, and most likely its atmosphere condensed in great rainstorms that formed the first oceans. From the interaction of the ancient atmosphere and oceans, there would arise a new force to help shape the planet.
We believe that in the early stages of Earth history, when the water was covering the Earth, the oceans would have been much more acidic. The atmosphere would have been made up of compounds like CO2, hydrogen chloride, very acidic conditions. The ocean, therefore, would have been nothing like it is today.
The oceans acted as a medium by which carbon dioxide could be converted into carbonates and carbonate rock formations, mainly limestones, which then sequestered most of the carbon dioxide originally emitted into the Earth's atmosphere. Carbon dioxide dissolves in rainwater and in oceans, forms carbonate rocks which sediment into limestone deposits. This then reduced the climatic impact of carbon dioxide in the Earth's atmosphere, reducing the so-called greenhouse effect of carbon dioxide and allowing the temperature of the Earth's surface to be fairly mild. By comparison, if we look at Venus, which has about 100,000 times as much carbon dioxide as the Earth's atmosphere, Venus has a hothouse surface of 700 or more degrees Kelvin as a result of all of the primordial carbon dioxide remaining in its atmosphere. The reason the carbon dioxide remains in Venus's atmosphere but not the Earth's atmosphere is because Venus probably never had large-scale oceans on the surface to absorb the carbon dioxide and convert it into carbonates.
One of the important roles that the ocean plays in maintaining the Earth's environment as we know it today is in the process we have termed the greenhouse effect. The Earth's climate is to a large extent determined by two processes. One is the amount of solar radiation that the Earth receives at the surface, and the second, perhaps important factor, is how that energy is retained by the Earth.
Visible radiation comes through the Earth's atmosphere very freely and tends to be absorbed at the surface. The sunlight is then converted to heat. That heat is then radiated away from the Earth, but at different wavelengths of energy. Now, whereas the atmosphere of the Earth is transparent to visible radiation, it is relatively opaque to this thermal infrared radiation. The gases that block this thermal infrared radiation include water vapor and carbon dioxide, among others. If, in fact, the Earth didn't have this greenhouse effect, then the surface temperature of the Earth would be something like 16 degrees below zero. In other words, the Earth would be frozen.
Liquid water on the Earth's surface nurtured the development of life. In turn, the chemistry of life altered the oceans and atmosphere.
One of the major steps in the evolution of the ocean took place at the time when oxygen was sufficiently abundant in our atmosphere and our oceans to allow minerals to exist in the ocean without being oxidized. And free oxygen was available for the metabolism of higher organisms.
Life could not evolve on the land surfaces of the Earth because ultraviolet radiation there was extremely intense. The early Earth had no oxygen or very small amounts of oxygen in its atmosphere. Accordingly, it had no ozone layer. Hence, ultraviolet radiation from the sun could beam down directly to the land surfaces and fry anything that happened to be down there. However, in the oceans, there could be debris, organic debris, floating on the surface, which would protect underlying organisms from the ultraviolet radiation, while at the same time allowing enough visible radiation to filter through so that organisms could begin to evolve using photosynthesis, that is, using sunlight as a source of energy.
Perhaps the next most important step in the evolution of the oceans took place when there was sufficient oxygen buildup in the atmosphere and oceans to allow organisms to inhabit land. This took place certainly many hundreds of millions of years ago, but relatively recently in the history of the Earth.
The photosynthetic organisms in the oceans would emit oxygen as a byproduct of photosynthesis. The oxygen would evaporate into the Earth's atmosphere and accumulate there. And eventually, after perhaps 1 billion years, enough oxygen would accumulate to produce a substantial ozone layer that would filter ultraviolet radiation from reaching the Earth's surface. At that point, life could move out onto the land surfaces and proliferate. And today, most of the living biomass is on the land. All of these factors have produced a climate that's very stable, that's very benign, and this has allowed human civilization to evolve and develop over the last 10,000 years. But 10,000 years is just a small drop in the bucket of all time in the solar system, and the survival of human civilization will depend on that favorable environmental state sustaining itself over a much longer time. This is why it's essential that we study the planet as an organism, if you will, an interactive system of solid Earth, of oceans, of atmosphere, and of living organisms.